Do you know how to turn these fans on?
You want them on?
Yeah, maybe.
On?
Yeah?
Okay.
How do we do it?
All right. Fans.
Well, that's the second row. Oh, maybe these ones. Oh, yeah, okay. Easy.
It's just on off or on
I guess
zero speed?
There's probably several speeds.
Okay. All right, so our colloquium speaker this week needs no introduction here. So Professor Norman Wildberger will tell us about primes, complexity, and computation, how big number theory resolves the Goldbach Conjecture.
Thanks, Lee. Well, thanks all for coming, and also welcome to our international guests who might be watching the live stream on YouTube. So today I want to reorient some things. We're interested in prime numbers primarily. That's really the main topic of interest. Prime number, well, let's first of all define it. It's a number, natural number n bigger than 1 is prime, precisely when it's not divisible by any natural number m, where m is between 1 and n. And in 1742, Christian Goldbach, in a letter to Euler, conjectured that every even number, n bigger than 2, can be written as the sum of two primes. So we can write n as p1 plus p2 for some primes p1 and p2. So in this talk, what we want to do is we want to give a review of some of the perhaps elementary aspects of prime numbers and their distribution. And I want to outline a new framework for thinking about, well, big numbers especially. In particular, I'm interested in notions of complexity and computation. So my point of view is I'm going to be doing things a little bit sort of orthogonally to the main thrust of research in this direction. And I'm thinking that if we go to big numbers, we sort of get to a place that's almost like a blind spot for current number theory. And it's that area, that very, very big domain, that we're going to find some interesting insights. And then I want to show that Goldbach's conjecture is indeed false. In fact, it's strongly so. So it's strongly false. That means I don't actually have to create a very sophisticated argument. I'll be able to use basically common sense and basically some back-of-the-envelope calculations. But there will be some philosophical aspects that I think will also be interesting. Okay, so the prime numbers are, of course, important because of unique factorization, which goes back to Euclid. The fact that every natural number is a product of prime numbers, and in fact, uniquely. And let's just remind ourselves of the basic strategy, simple-minded though it is, of proving such a thing. If you have a natural number n and you want to write it as primes, well, you just start dividing it first by 2 and then by 3 and then 4 and 5 and looking for a divisor. And if you get to a number r with r squared bigger than n, you can stop and conclude that the original number was prime. And otherwise, you'll have found a prime divisor. At which point you take the prime divisor and you divide the number you started with by that prime and start all over again. And you just sort of repeat. And you eventually get at a product of primes. And proving it's unique is a bit more subtle. And at this point, I just want to pose this question. It'll make a little bit more sense later on. Does this proof really work for big numbers? Just want to put that out there. It's a question. OK, so here are some examples of prime factorizations. I have a particular sort of affinity for numbers of the form 10 power of 10 plus 23. So here's 10 cubed plus 23. It's factorization 10 to the 5th plus 23, 10 to the 10 plus 23, 10 to the 50 plus 23. And this one here, my computer struggles to find that one, 10 to the 100 plus 23. You can test your computer skills. So it's a little bit hard because there's that big prime there followed by that big prime. Whenever you have two big primes multiplying, it's generally challenging for computers to find things. And of course, 3 is a factor for all of these things because the sum of the digits is divisible by 3. OK, see, the other main really important key fact about prime numbers also goes back to the ancient Greeks, and this is the role of Eratosthenes' sieve. So Eratosthenes was the brilliant chief librarian at Alexandria, who was also famous for first having measured the size of the earth. And he had a way of actually generating primes through what's called a sieve. And let me just remind you, you start with numbers and you remove 1 out of consideration. And then you start with the first empty spot, which is 2, and you remove all multiples of 2. And then you go to the next one, which is 3, and you circle it, and then you remove all multiples of 3, which are already not removed. And then you go to the next one, which is 5, and you remove all multiples of 5, which have not already been removed. And then you go to 7 and remove all multiples of 7, and so on. And so already at this stage, we have enough information in this final diagram to read off what the primes are that are less than 100, because if a number is not a prime, then it will be divisible by something less than square root, so one of the primes, 2, 3, 5, and 7. So there's a list in white of the primes less than 100. And this is his sieve, and this is really at the core, even today, of modern attempts at computing with prime numbers, and also sort of theoretically as well. OK, so let's just observe some elementary facts. That the pattern of multiples of 2, 3, 5, and 7, this is periodic with period, the product of the 4 numbers, which is 210. So in other words, if you're only concerned with divisibility, mod 2, 3, 5, and 7, everything repeats with a cycle of 210. And there are then 5 210, this is Euler's phi function, which is 48 numbers in the range 1 to 210, which are relatively prime. And the formula is you take 2 minus 1 times 3 minus 1 times 5 minus 1 times 7 minus 1. And the reason for that is basically inclusion-exclusion. So if you take this product and you write it out just using the distributive law, then the first thing will give you the number n itself. And then the next things are these are removing the multiples of 2, 3, 5, and 7. But then you have to add on the multiples of 2 and 3 that you've already done, that's there, and then the multiples of 3 at a time, and then the multiples of 4 at a time. So this formula is really just inclusion-exclusion. It's just the formula for the number of numbers in the range 1 to 210, which are relatively prime to 210. OK, so we can take those numbers and we can divide by the product to find the proportion of numbers which are relatively prime to 2, 3, 5, and 7. And we can easily just sort of apportion each of these primes to each of the factors, and so we can rewrite that as 1 minus a half times 1 minus a third times 1 minus a fifth times 1 minus a seventh. So that's 48 over 210, or 8 over 35. And so this is the probability that a number is not divisible by 2, 3, 5, or 7. I have a little bit of a throat here, so I have to. And pleasantly, this kind of formula alerts us to the fact that relative primeness is, in fact, an independent property, in the sense that if we had just sieved 2s, 3s, and 5s, and then we were, with the numbers that were remaining that were relatively prime to 2, 3, and 5, we were then chopping up or looking for multiples of 7, we would end up removing each 7th one. So they're all independent of each other. That's a consequence of this factorizability that we see directly here. Okay, so maybe we're interested in the primes less than 100. What's the probability of having something be relatively prime to a number less than 100? Well, then we could just take the same product, 1 minus a half, 1 minus a third, we'll go through all the primes up to 1 minus 197, and that turns out to be this number here. So this is the probability that a number is relatively prime to the primes less than 100. And this is a real probability in the sense, I mean, often when you're talking about natural numbers, it's a little bit dubious or questionable what you mean by probability, because it's, after all, an unbounded set. But this is actually a very precise meaning of probability, because everything is periodic, in this case, with period, the product of all these primes. Okay, so this number that we've just calculated is roughly 0.120317, which is telling us that if you pick a number at random, there's basically a 1 out of 8 chance that it's relatively prime to the numbers, the primes less than 100. In other words, it's about a 1 out of 8 chance that it does not have a prime factor less than 100. And that's a very precise statement. And it's related to a very beautiful classical formula of Frank Merton's in 1874, which is a key sort of precursor of analytic number theory before the prime number theorem, which is that the limit of log n times the product of all primes less than n, less than or equal to n, of this exact thing that we're interested in, 1 minus 1 over p, that product has limit e to the minus gamma. Gamma is Euler's number, and this e to the minus gamma is a number which has a value 0.561459 approximately. All right, so that means, for example, if, say, n is equal to 100, that's telling us that this product here that we just calculated in the previous page could also have been estimated by taking the ratio of e to the minus gamma over log 100. So basically 1/2, roughly, over log of n is the probability that you've got a number, that an arbitrary number has prime factorization with no primes less than n. That's a very beautiful fact, and it's pre the prime number theorem. It's a pleasant kind of thing. Okay, so if we're interested in counting primes, which is a natural thing to do, then pi of n is the number of primes, and we've already talked about pi of 10 equals 4, the primes that we've already talked about, and pi of 100 equals 25. And here are some other values of pi. The first known list of primes is that of Cataldi that goes back to 1603, which gives the least prime factors of numbers up to 800. In 1746, Kruger published a table of primes up to 100,000, and so that would have been accessible to Legendre and Gauss. And they were very interested in tables of primes. These days, lists of primes are basically unnecessary, and you don't actually find them. If you want a list of the prime numbers, up to 1 trillion, you're going to have a hard time finding it, because computers themselves are so efficient at generating such lists. Basically, your computer can calculate such a list almost faster than it can load it from some external device. So, for example, in 1980, the well-known Australian number theorist and computer scientist Richard Brent needed the primes up to 4,400,000, and so he just computed them and then discarded them. There's no need for keeping it around. Okay, so this number pi of n is sort of crucial. It's the heart of questions about the primes. And it's interesting that there's a sort of indirect method of trying to get at these things. So for example, suppose we go back to the primes that we've already been talking about and look at n equals 2 times 3 times 5 times 7. If we look at all the numbers which are relatively prime to n up to 210, that includes all the primes up to 210, except for 2, 3, 5, and 7. along with a few others. So the total number of numbers which are relatively prime to 2, 3, 5, and 7 is 48. We've calculated that already. And that's going to be then the number of primes less than 210 minus 4, because we have to subtract the numbers 2, 3, 5, and 7. They're primes which are not in here. We have to add 1 because we haven't included the number 1. And we have to add 5 because of these 5 numbers. These are products of primes that are still under the ceiling of 210, but are generated by primes bigger than the ones that we're considering. Okay, so we can list them, we can find them all, and then we can therefore solve this formula and find that pi of 210 is 46. So we found how many primes there are up to 210 without actually sieving all that way. So it's kind of an indirect technique. And so such thinking was used by Miesel in the 1870s, more sophisticated, but to find pi of n for some large n's. And his methods have been extended and refined by people over the period. And so now we have, I think this is the record holder. Now we know that pi of 10 to the 25 is this number here. And this is 1, 2, 3, 4, 5, 6, 7, 8. So that's 24 digits. So we're talking about a number with 25 zeros, and so it's a reasonable fraction of the numbers less than this are primes, in fact. So there is lots of primes. What about the largest primes? Well, before computers, the largest prime was 2 to the 127 minus 1. That was known by Edward Lucas, who was an important number theorist, and developed some important tests for primalities and such. So these days, the current record is this Mersenne prime. These are all primes of this form 2 to some power minus 1. That's called a Mersenne prime. And typically, as you can see from this chart, Mersenne primes tend to be the record holders in terms of the biggest primes. So these are the recent record holders. This one here was only January 2016, so it's 2 to the roughly 74 million minus 1. And the previous one was 2013. That was 2 to the 57 million. So you see, that stood for quite some years. That stood for 3 years. These were all pretty well found by the GIMPS system. So this is the great internet Mersenne prime search, which you can join if you like. You can get your computer while you're doing something else to work on finding Mersenne primes. There's thousands of people doing this. And so it's interesting, I think, that despite the increases in computing power and memory and so on that we've had in the last 20 years, you can see that we've made significant progress, but maybe it's not quite as stellar as you might have imagined it might be. Right. So we got from 2 to the 13 million to 2 to the 74 million. Okay, maybe the other thing that I have to mention is we have to talk about the zeta function, at least mention it, even though it won't play a big role in this talk. So this formula up there is a formula that I kind of like because it involves things like that I have a lot of affinity with, which are multisets. So I like to think of a lot of mathematics as built up from multisets. So, so it's like a set with multiplicities. So on this side here, you see all the natural numbers, and over here you see the powers of 2 and powers of 3, powers of 5, powers of 7, and so on. And if you take those sets and you multiply them in sort of the obvious way, then there's an equality of multisets. And that's basically the statement of the unique factorization of Euclid. That's just another way of stating it in terms of sort of a set theoretical point of view or combinatorial point of view. Now, if you take that same formula and you raise, excuse me, you raise every number to the rth power, let's say, then the multiplicative aspect of it will mean that it's still a correct identity. And then if you sum all the things that you find on this side, well, you get the sum of n to the r. And then if you think about what you get over there, you have basically geometric series. So the first one is 1 over 1 minus 2 to the r and 1 over 1 minus 3 to the r. So this is basically Euler's formula for the zeta function. Although it's typically when it replaces r with, say, minus s to get this having the more familiar form sum of 1 over n to the s. That's the zeta function. And it's amusing, if I look at this thing here with the r equals -1, then I get 1 over 2 and 1 over 3 there. And if I take the reciprocal of the whole thing, I get the harmonic series to the -1. And on the left-hand side, I get the product of exactly the kinds of things we've been talking about earlier. So you have to interpret this correctly because we know the harmonic series diverges, so this is really logically 0, and this is saying that this product here should be 0 in some sense. But it certainly implies that there can't just be 4 primes, for example, because if there were just 4 primes, then there's no way we're going to be getting 0 out of this thing here. So this is kind of observation of Euler that you could extract the infinite aspect of primes from these kinds of considerations. Okay, and then we come to the big theorem in the subject, which dominates the entire subject, which is the prime number theorem, which is, and it goes originally back to Legendre, who conjectured that pi of n is about n to the log n over log n. Actually, he conjectured something which is a little bit more like n over log n minus 1, which is a little bit better. And the tilde means that the ratio of the two things goes to 1. Okay, so Gauss realized that this had a probabilistic aspect. It's sort of telling us that the probability of having a prime number between 1 and n is roughly a log n. But Gauss realized that it was probably better to phrase it in terms of the probability of being prime close to n as 1 over log n. Not in the whole interval, but just close to n. In which case, then one replaces that with 1 over log x and integrates from 2 to n. So this is the Lie function, and this is another approximation to pi of n. And then the great theorem of Hadamard and de la Vallée-Poussin in 1896, which actually establishes this asymptotic formula for the number of primes less than n. And here is something of a picture for up to 200. So the red line is x over log x. The blue line is the Lie function. In here we have the rather ragged pi of x function. And in green is something I haven't told you about, which is a more sophisticated approximation due to Riemann. Okay, now the prime number theorem is all very nice, but it doesn't really tell you what you want to know explicitly in explicit situations. For that, what you really want is bounds. And so analytic number theorists are very interested in explicit bounds on things. So in 1961, Rosser and Schoenfeld proved a nice thing that's easy to remember, that pi of n is actually between n over log n minus a half and n over log n minus 3/2, at least if n is bigger than 67. So this gives actually a bound on either side that you know pi of n is in there, even for smallish n. And it's easy to remember because if you remember Legendre's approximation n over log n minus 1, then this one is sort of symmetrically displaced around that. Okay, and I would like to just quickly mention to sort of bring us on to the next topic is Skew's number, actually Skew's second number. So for most numbers in the range we're familiar with, the Lie function dominates pi of n. The integral of 1 over log t dominates pi of x. But for example, the trillionth prime is that one there, so pi of this 29 trillion zone is exactly 1 trillion. And the Lie function of this same number is a little bit more than that, okay, showing that the Lie function is bigger than pi of n, just like that graph that I showed you earlier. And certainly it suggests that that might always be the case, but it turns out that it's not. So that Littlewood in 1912 showed that eventually pi of n actually goes higher than the Lie function. And his student, Skew's, actually found a bound saying when that actually occurs. We don't know exactly when it occurs, but it occurs at some point before we get to 10 to the 10 to the 10 to the 964. Remarkably, excuse me, remarkably, this transition or this oscillation between Lie and pi occurs infinitely often. They alternate. One is bigger than the other infinitely often. All right, so this is a very big number. It's hard to get one's head around this, but this sort of leads to the next thing I want to tell you about, which is sort of our point of view, which is that we should really think about the numbers on a very large scale. Okay? So I'm proposing that it's natural to think about numbers in perhaps 3 different kind of categories. One, in a very primitive way, that a number is just a bunch of strokes on a page. And in a sort of second, sort of middle-sized arena, that a number is a familiar Hindu Arabic number that we all know about. And then there's this big number theory, or this sort of bigger picture that's out there, where we deal with number expressions. For example, this thing here. Okay, so if we stare at this for a second, this is a big number. What's inside the brackets here is just doable on your computer. So your computer, you could input that on your computer and it would tell you what that is. But if you raise it to this power, then it's beyond, the computer can no longer tell you what that is. It can no longer work with it. It's too big. Okay, but we can still talk about this. We can still talk about multiplying this thing here. And then there's something else that's a little bit strange, which you don't know about yet, but I will tell you about it shortly. Okay, so I guess maybe of all the talk, this is really the heart of the matter. Okay, this is really the essential point that I want to get. If you remember one thing about this talk, please remember something in this direction. It's that the definitions, intuitions, theorems, and proofs that we have developed for small and medium numbers break down. They break down as we move further into big number theory. That's a fact that I hope to convince you of. All right? I hope you will see that as, yes, a very plausible fact. Okay, so let's get used to thinking a little bit about big numbers by starting with some medium-sized numbers. So there's about 1 trillion stars in our galaxy. There's approximately 1 trillion galaxies in the known universe. That's a pretty big number. The number of seconds in the known universe is this thing here. Number of particles, roughly 10 to the 90. And this one is especially important for us. The number of Planck cubes in a meter cube. Okay, so nuclear physicists are able to resolve things down to a certain scale, and after that they cannot get any further down. And that's generally a Planck scale. So if you imagine the smallest possible cube that you could possibly resolve, even very optimistically, there's roughly about a googol of them in a meter cube. Googol is 10 to the 100. And remarkably, there's also roughly about a googol number of meter cubes in the known universe. So we are somehow poised geometrically between the very small and the very big. And it's that googol number that controls both of them. So interest in big numbers goes back a long time. And Archimedes, the greatest mind of all time, in my opinion, was very interested in this. And he wrote a famous thing called the Sand Reckoner, where he proposes to calculate the number of grains of sand that could fill the known universe at his time. And he, interestingly, used a model of the universe that was heliocentric, that had the sun at the center, and had the stars out here. And he said, let's calculate how many grains of sand we could put in this universe. And in order to do that, he had to really develop an arithmetic that went far beyond what the Greeks had at that time. So the Greeks did not have a very sophisticated arithmetic. When they wanted to do sophisticated arithmetic, they invariably borrowed the Babylonian system that was 2,000 years earlier to theirs. But so anyway, he invented some system, myriads, and eventually concluded that it is therefore obvious that after a lot of calculation, that the number of grains of sand filling a sphere of the size that Aristarchus lends to the sphere of fixed stars is less than 1,000 myriad eighth numbers. So he has some tower of numbers and some system. And when converted into our system, that's about 10 to the 63. Okay, another famous big number, quite a lot bigger, is what's called Graham's number. And this comes from Ramsey theory, which is a subject that often has big numbers involved. Okay, so the question is actually quite a simple one. You have a cube, or possibly a hypercube, a cube in higher dimensions, and you paint all the edges, one of two colors, and you look for a slice, a planar slice, where you have a complete 4 of the same color. Okay, so this particular color has such a complete 4. If you look at these sort of front 4 vertices which all lie in a plane, you see that all 6 edges are blue. So this coloring does have such a thing. But if I change this top color here to a red, then there would be no longer such a complete 4 in this graph. So the question is, how big does the dimension have to be to guarantee that no matter how you color the edges of a hypercube, you always have a complete 4 in it of a single color? And Ronald Graham gave an answer to this, and that was published by Martin Gardner in 1977, so it became rather notoriously famous and became known as Graham's number. So it's some iterate of some function, and the function itself depends on some kind of strange operation, either in terms of some arrow or something else. So f of k is 2 arrow k 3, and then you have to iterate f of 12, f of that quite a few times. So this is a humongously big number. But what is this new operation, or what are these new operations? So we have to talk about hyperoperations now. So we want to move number theory into the big realm. Okay, we want to get big numbers. So to do that, we need more powerful operations. In the same way that we go from addition to multiplication to exponentiation, we know that increases our numbers. We want to go further. So let's look at the 3 operations. So here, note that multiplication can be defined inductively from addition. M times 1 is m. And m times k plus 1 can be defined in terms of m times k by m times k plus 1 is m plus m times k. And then exactly the same kind of definition allows us to define exponentiation in terms of the prior operation of multiplication in an inductive way, so that m to the k plus 1 is defined in terms of m to the k. So once we understand that addition to multiplication is exactly the same as multiplication to exponentiation, then of course we should just carry on, right? And that's what these hyperoperations are. So the next one is what I like to call the triangle operation, but it's also called tetration, and it's exactly the same thing. So m triangle 1 is always m, and then m triangle k plus 1 is m to the m triangle k. And what's it look like? Well, there's the definition again, and it's not too hard to convince yourself that this is what they look like. So in general, m triangle k is an exponential towers of k copies of m. Okay, the number 10 triangle 4 is particularly convenient. So there's 10 triangle 4, because this bounds the total number of expressions that are possible in the known universe if we write at the scale of, if we allow ourselves to write at the scale of Planck cubes, and we have, let's say, 1,000 symbols. Because how many Planck cubes are there? Well, we've seen that there's 10 to the 100 in a meter square in a cubic meter, and there's 10 to the 100 such meters in the universe. So there's 10 to the 200 such Planck cubes in the whole universe. Up, right there. And if there's 10 cube things that can be put in any one of these 10 to the 200 places, then that's the number of possible expressions that we can write down. That's assuming that we can write at this very small scale. And if we were able to write at this very small scale, then we could fit all of humankind's digital information in this little box here. So it's a very efficient way of writing. Okay. But if we could write at that ridiculously small scale, then 10 triangle 4 is an upper limit to the number of expressions that we're able to write down in the known universe. Okay, so this hierarchy of operations can be extended. So you can take the successor operation of any operation. And it's defined exactly the same way. You define the successor star prime in terms of the original operation star in an inductive way, exactly the same way as all the previous examples. And then you get a list of, or a sequence of operations, the first being addition, and then multiplication, and then exponentiation, and then triangle, and then star 4 and star 5, and so on. And this is where the symbol m star r comes from, or m using Knuth's arrow notation, m to the r minus 1k. These are basically the same. It's just a name for this kind of very high-powered arithmetical operation. And it all really goes back to work of Ackermann in 1928, who defined this thing basically as a function of three things, m, k, and r. And it's since been utilized and massaged and exploited in lots of ways. So Goodstein in 1949 explicitly introduced the idea of hyperoperations. Knuth introduced up arrow notation. Conway introduced chained arrow notation. Oh. Okay. What does that mean?
That has to be very
out of range. That's great. Okay.
You were loading the PDF from your
Was I loading it from the? Oh, maybe I did. Okay, it should be on the. I pulled the thing out. Okay, so while Joshua was helping us get that together, so what are we going to do? We're thinking about these bigger numbers. We've got these bigger operations, and now we're in a position to. One more? Right, to write down some interesting numbers. Okay, so this first one is Z, which is 10 triangle 10 plus 23, okay? And then that's a big number. And then here is some other, some even, this one is 10 star 5, 10 plus 23. That's the 1, 2 further on. So you have a row of 10s and then a tower of 10s, and the number in this tower is number this tower, and the number, there's all these successive towers of 10s, and the number in here is also equal to something like this. And so you have to read this from the top bottom, and you can stare at this for several days, and then you'll get a big headache trying to figure out, trying to imagine just how big this thing really is. Okay, so but one can so there's a whole sort of zoo of people out there called Googologists who are interested in creating big numbers. And so basically what we can do is we can introduce something a little bit more organized. So this is my own take on Googology, I suppose. So one can define a limit operation. So once you have a sequence of operations, you can define a limiting operation by the rule here that m star k is m star k k, where you use the second entry as both an index and as an exponent. And that then allows you to create new operations from hierarchies. Okay, so I'll just quickly go through this. So if we go to star n, by the way, so star n is the definition, is the limit of the star k's that we've introduced in Ackermann's thing. So star n is now a new operation, which is the limit of the Ackermann ones. And then we can take its successor, and it turns out that star n plus 1, that's this thing that has a chain aspect to the actual things that index the stars, and so then 4 star n plus 100 easily exceeds Graham's number. So, but we can keep going. So we can take successors, and we can basically do the same kind of thing that one does in ordinal set theory. So you have sequences of operations, and you can take limits of sequences, and then you can take new successors and new limits. And so you get these huge kind of thing. And eventually, for example, you could get star n squared. And so there's a calculation that I make in my Math Foundations 180 video. So calculating 3 star n squared for, okay, it's some ridiculous thing contains some ridiculous thing, and here is 3 star 3, 3, 3, 3, 3. So this all is already far exceeding Ackermann's thing, and then that ends up being input into that and there. So one just has to use various superlatives. This is completely beyond us in terms of understanding what's really going on here, in terms of getting at such numbers. But one can write, or we can write them down. So in fact, you can get a very pleasant hierarchy of arithmetical operations, which completely mirrors the standard ordinal set theory setup. But now these are operations and not sets, and so they're in principle actually specifiable by a computer. So I think it's actually a very interesting programming challenge for computer scientists to actually see how many of these things could actually be programmed. So these are programs that you can't really run. So as soon as you try to run them on anything, your computer just takes up all the room in the universe and has, without giving you an output. But nevertheless, you can write the programs. Okay, now, if you contemplate these kinds of numbers for a while, you start realizing something. You start realizing that arithmetic in this realm becomes very, very onerous. That things which are very simple back in the small and medium framework become hard. Even identifying when two numbers are, which one is bigger? Here are two numbers. Which one is bigger? This is highly non-trivial in this realm, because we don't have standard ways. You can't just take some expression like this and reduce it to a Hindu-Arabic thing because it doesn't fit on your computer. And then even the definitions, the definition of these various things are all problematic. How do you define addition or multiplication or exponentiation? And that's long before you even get to some really sophisticated numbers like these ones. So basically, we have serious problems doing any kind of real arithmetic at the big number scale. Okay, so now there's another aspect of this that I want to talk about, which is complexity. So we've talked about the computable aspect, now complexity. So complexity is a measure of how efficiently you can write down something. So let's introduce this particular notion of complexity. Let's start with these operations. We're just going to use addition, multiplication, exponentiation, and the triangle operation. Forget about all the others. We'll use the digits from 0 to 9, and we'll use 2 brackets. That's a total of 16 symbols. And then we'll say that the triangular complexity, C of n of a number, is the minimal number of symbols you need in order to write down a legitimate mathematical expression that evaluates to that number. So C of 81 is 2 because it takes 2 digits. C of 665 is 3, it takes 3 digits. C of 1023 is 4 because it takes 4 digits. But C of 1024 is 3 because you can write 1024 as 4 to the 5. That's only 3 digits, 3 symbols. This number here, its complexity is certainly less than or equal to 9 because it happens to be, because I chose it that way, 435 to the 12 plus 17. So it's how much room you need in order to write down a number in the most efficient possible way, given that you're allowed to use addition, multiplication, exponentiation, and the triangle operation, and brackets. Okay, so here's what I would like to call the complexity compression theorem. Okay, so this is a statement. The question is, how difficult is it to compress a number to within half of its natural size using these k equals 16 symbols? So I have a big number with this many digits, and I'm interested, can I compress it to, say, half its size? And the theorem is that the probability p that a natural number n with 2m digits, the probability that that has a triangular complexity less than or equal to m, so going from 2m to m, that probability is less than 2 over 2 to the 2m. Okay, and here's the proof. Okay, so we want to estimate this probability. So here's the total number of numbers that we're interested in, the numbers with at most 10 to the m digits, 2m digits, that's 10 to the 2m. The numbers with complexity at most m. So I don't need to restrict myself to numbers in this range. I'm just going to consider all numbers with complexity at most m. And then their complexity can be, well, if they have 1 digit, then there will be one of them if there's 1, 2, up to m digits. So the number of numbers with m digits, if the digits, you have k choices, is k to the m. So we estimate this like this. We have a little geometric series. We replace the k minus 1 with k over 2 because k is 16. We do a little bit of manipulation. We replace k with 16, and we get 2 over 2 to the 2m. So what's this telling us? It's telling us that if you have a number with 1,000 digits and you want to know what's the probability that you can compress it to 500 digits using this system, the probability is very small. It's a very small probability. Okay, and what if there were more than 16 symbols? Suppose you had 10,000 symbols. Well, there's a corresponding result, which is sort of analogous. Okay, so now we come to a crucial diagram, okay, which is a kind of a fairy tale diagram, really. But nevertheless, it's instructive. So this is from one of my YouTube videos. So here is the number n. And here's the complexity of n. And the number n is going from 1 up to z, which is roughly 10 triangle 10. Okay, so what's going to happen to this complexity? Well, if you have a number 10 triangle 10, the complexity is typically the number of digits that you need. And this is 10 to the 10 to the 10. There's the log of that is basically 10 triangle 9. That's the exponent of 10. So the complexity is roughly 10 triangle 9 for most of these numbers. If you just pick a number in there, it'll be 10 to the 10 digits long, and its length will be 10 triangle 9. And we know that from the previous thing that the probability that we can compress that number to within 1/2 of its number of digits is some minuscule number. So to be able to compress the number down to just 10 triangle 9 over 2 is almost impossible. What's this telling us? It's telling us that the vast majority of numbers between 1 and z are completely inexpressible to us, because the known universe is just contained in 10 triangle 4. Right? We've seen that the maximum number of possible expressions that we can write down in our universe is 10 triangle 4. That's an upper limit. That's how much size we have to. So the most of these numbers have huge complexity. It means they're completely invisible to us in our known universe. Most numbers less than z cannot be written down in our universe with our 16 symbols. And even if you allow 3,000 symbols, it's not going to change things appreciably. Okay, so now some conclusions of this, or some arguments. So first of all, it's impossible to factor z into prime factors. It's impossible. Absolutely, completely, and utterly, hopelessly impossible to factor z into prime factors. Most of the prime factors, first of all, are these dark numbers. I mean, most of the numbers in this range we cannot see, right? They're so complicated we cannot write them down in our known universe. Let's call them dark numbers. So most of the primes are going to be of that kind. There's no way you can write them down, even if you knew what they were. But another serious problem is that the complexity of successive quotients, as we find more and more prime factors, blows up beyond the bounds of the universe. So let me illustrate that. So on the internet, on my Math Foundation site, I talk a lot about this number z and these kinds of things. And so I've given this as a challenge to my viewers to find as many prime factors of z as we can. And this is a very interesting computational problem. And we know, thanks to Joel Sjögren and others, that we have some prime factors of z. Okay, I remind you, z is 10 triangle 10 plus 23, that specific number. And we know that we have these 1, 2, 3, 4, 5, 6, 7, 8 prime factors that you can find just by using modular arithmetic in a very clever way. So there's these 8 factors, and then there's w, the quotient. What happens to the quotient? Well, when you divide z by these 8 primes, it's a lot like taking the reciprocal of the product, because z is basically 1 followed by a quadrillion zeros. It's like taking the reciprocal. And if you just take the reciprocal of the product of these 8 things, then you may know that when you take a reciprocal of a natural number, you're getting some decimal that has some repeating thing. And you can calculate how long that repeating thing is. And if you do that for these things here, you find out that the repeating cycle has a length of precisely this. This is due to Andrew McKinnon's calculations. This is a number that would require 10 trillion terabytes to write down. So total internet traffic these days is about 1 billion terabytes a year. So we're talking about 10 trillion terabytes to write down the repeating decimal that you get when you try to compute this thing here. So you see the problem that if you have a 1,000-digit number, and you want to factorize it into primes. So you get your computer, and maybe it's lucky and you find a prime factor. So that means that instead of having a 1,000-digit number, now you have a 950-digit number. The problem has become slightly simpler. With every prime that you find, things are becoming simpler. Here, it's exactly the opposite. With every prime that you find, the problem gets more intractable because the quotient's complexity is going through the roof. Right? We started off with a number z whose complexity is very small, even though it's very huge. But as we find more and more prime factors and we want to divide by those prime factors, the remaining stuff is becoming completely impossible for us. So z does not have a prime factorization. Was Euclid wrong? No, Euclid was not wrong. His notion of number just did not extend to numbers such as z. So Euclid was to a number, Euclid was interested in numbers that look like this. This was a number to Euclid. It was a line segment. Okay, so arithmetic to Euclid was like this. There's one line segment, and there's another line segment. What's their relationship? Maybe this one's 5 times this one, or maybe it's 23 over 4 times this one. So to Euclid, the question of how you can factor z would be completely a nonsensical question because you can't exhibit z as a line segment. That's not the kind of number that Euclid was concerned with. What about Euclid's argument about primes past z? So we all know that there are supposedly an infinite number of primes. Well, let me tell you, my friends, there are not an infinite number of primes. Okay? There aren't. Let's suppose that we want to argue, as Euclid did, that there's a prime number past z. So what are you supposed to do? You're supposed to, first of all, find all the prime numbers less than z. That's step 1. Step 2 is you construct the product of all those primes and add 1. And then step 3 is you find a prime factor of that. All of those are completely and utterly, hopelessly impossible for z. The universe is too small to do that with our current understanding of how big the universe is. It's nothing to do with our computers and their limitations. It's a question of the capacity of the universe to compute something. Okay, so I'd like to mention Jim Franklin, who is the architect of this new Aristotelian realist philosophy of mathematics, which has had a great influence on me. I really feel this is a really important development in philosophy. So most of us mathematicians are closet Platonists. We believe that there's this fantasy arithmetical world somehow beyond our own universe, and that what we're doing is some kind of reflection of that. But Jim says, no, let's think of mathematics as being based actually on this world that we're actually living in, and that we're talking about basically applied mathematics. We're talking about formulas, we're talking about patterns, we're talking about objects that are actually in our world. So here's a quote from him. The aim is to create a complete philosophy of mathematics based directly on applied mathematics, taking the view that mathematics is not about otherworldly entities like numbers or sets, nor a mere language of science, but a direct science of structural features of the real world like symmetry, continuity, and ratio. So, fact, I claim, it's impossible to write down or express a prime number bigger than z. You're just not going to be able to do it. You're not going to be able to write down or express a prime number bigger than z. And I think this is really, it's instructive to contemplate Niels Bohr's statement about physics and the role of physics. That physics concerns, the task of physics is to find out, it's wrong to think that the task of physics is to find out how nature is, he says. Rather, physics concerns what we can say about nature. And maybe we should think about mathematics that way too. It's really what we can actually say about mathematics. Okay, so the sort of the final now thing to moving towards the Goldbach conjecture is I have to give you a little lemma. So this is a very simple kind of thing. You flip a coin m times with the probability of a head being p. Then the probability of no heads is 1 minus p to the m. And so the probability of at least one head is 1 minus p to the m. And then we can use the simple inequality that for x positive, 1 minus x to the n is bigger than or equal to 1 minus nx. That's represented here for n equals 5, just taking the tangent to this little polynomial. So that means that the probability, this probability up here is less than or equal to 1 minus mp, and that's equal to mp. So we can summarize this in what we might call the needles in a haystack lemma, which is that if the probability of finding a needle is p, and you have m independent tries, then your chance of finding a needle is less than or equal to mp. So for example, if 7,000 out of 7 billion Sneetches are secretly awarded stars, and you get to pick names randomly 100 times, you're trying to find a name of a Sneetch with a star, then the probability of getting at least one starred Sneetch is less than or equal to, there's the number of tries you have, and the probability of getting a starred Sneetch is 7,000 out of 7 billion, which is 1 over a million. And so your probability is less than 1 over 10,000. Okay, so why is it that you can't find primes bigger than z? So if we believe in the prime number theorem, or in fact Merton's theorem, then the probability p of a number n bigger than z being prime is, what's the probability of a number bigger than z being prime? It's less than or equal to 1 over log z. You can either use Merton's theorem or the prime number theorem. And log of z is about 10 triangle 9. We know that there's at most m, 10 triangle 4, numbers that can be expressed in the known universe. So there's at most this number of numbers bigger than z that can be written down. You can't write down more numbers than that. So the probability that at least one of these is prime is less than m times p by the needles in the haystack lemma that we've just proven. So the probability that there's a visible prime bigger than z is less than or equal to 10 triangle 4, that's the m, times 1 over 10 triangle 9, that's the probability. And 10 triangle 4 is a big number, but 10 triangle 9 is just so much bigger. So this whole thing is less than or equal to, say, 1 over 10 triangle 8, which is effectively 0. Human beings cannot detect the difference between that. The probability of having a prime bigger than z is effectively 0. It's basically saying, in engineers' terms, it's impossible to write down a prime number bigger than z. And so the Goldbach conjecture is false. Consider n equals 2z. That's an even number. If this even number is a sum of two primes, then one of them is bigger than z. But it's impossible to write down a prime bigger than z, so it's impossible to write z as a sum of two primes, so the Goldbach conjecture is false. In fact, it's strongly false. Okay? So if it were true, and you actually wanted to write down 2z as a prime, a lot of miracles would have to happen. First of all, you'd have to find a prime bigger than z, which is less than 2z, which is basically impossible. And then you'd have to require that 2z minus p, the difference, is also prime. Another complete impossibility. And if those two miracles just happen to line up by some kind of incredible fluke, which is probably roughly comparable to all the atoms in the universe arranging themselves tomorrow morning to form a giant teapot. All right. If that actually transpired, then you still have to work exactly the same miracle again for 2z plus 2, and then 2z plus 4, and 2z plus 6, and so on, and eventually also to these much bigger numbers for which everything is completely, even more ridiculously hopeless. So basically, the big numbers just defeat things. There's no way that you're ever going to be able to write down 2z as a sum of primes. Okay, I did have some slides here on the history, but it's somehow sort of a little bit tangential. I might mention that in 1995, Ramar showed that every even number greater than 10 to the 30 is a sum of at most 6 primes. It's sort of a famous, relatively recent thing. And in 2012, Terence Tao showed that every odd number is the sum of at most 5 primes. And I also want to mention that Oliveira e Silva verified the even Goldbach conjecture, that's the one we're talking about, up to about 10 to the 18. Okay, so In fact, once you start thinking about this, you know, and you start really sort of realistically looking at big numbers, you realize that a lot of these other conjectures are also going to just die. I mean, there's not going to be any twin primes beyond Z. Let's face it, right? You're not going to be able to find any primes beyond Z, so it's not going to be twin primes either. You're not going to find Mersenne primes beyond Z. There aren't any primes, in particular, there aren't any Mersenne primes. You cannot find primes of the form n squared plus 1 beyond Z. And the whole list could go on. Okay, so I think we need to rethink things, okay? We need to acknowledge that these number expressions, you know, these vastly incredible numbers that are created from these, you know, towers and towers of exponentials or even these other things, this is a domain of numbers that we don't necessarily really want to engage in. Maybe we want to restrict ourselves. So maybe we need to aim for a more restricted mathematics where we restrict to natural numbers, which are primitive natural numbers in this very simple-minded way, or Hindu Arabic numbers of this kind that you can actually write down. If we do agree to restrict ourselves to only those kind of numbers, then all of these conjectures are back on the board. It's a completely different question. If you write down an even number in Hindu Arabic form, can you write it as a sum of two primes? That's in fact, I think, much more sensible thing to think about. Okay. So I think it's also, this argument is also showing us that it's really important to think about constructive arguments that actually exhibit mathematical truths and not just assert them. Okay, if you like this kind of thing, there's my YouTube page, and the Math Foundation series is all about these kinds of considerations, and there will be a lot more detail about some of the things that I've been talking about. Thanks for your attention.
So questions or comments?
Catherine.
Do you reject all non-constructive existence proofs?
Do I reject all non-constructive existence proofs? No, I don't. No, not offhand. I don't want to just throw everything of a certain kind out the window. I want to look at things and say, well, maybe that one, no. Depends. Yeah.
But you don't believe in the existence of a prime unless you can write it down?
I'm not saying I would go that far. No, I wouldn't say that necessarily. Peter.
Yeah, you're aware of the guy called Zhang or something.
Sorry?
Recently, a guy called Zhang came pretty close to the twin primes theorem, and the peloton following him showed that there's an infinity of primes, pairs of primes differing by at most 7,000 or something. So what you are saying would be in effect denying what is now an accepted theorem.
Yeah, so the question is, there's some recent results of asserting the existence of an infinite number of twin primes, or
They differ by it.
oh, but maybe not by differing by 2, by differing by 7,000. And would I object or not believe in such a thing? I would say that probably I would want to restate that theorem in a more specific, concrete way. Any theorem any statement that says there's an infinite number of this or that, let's say, is not going to immediately be, makes me comfortable. Peter.
I don't know, I'm very naive, but it seems that there's a confusion here between saying that something exists and we can explicitly find it. So you said that there is no prime number between Z and 2Z, and yet Bertrand's postulate tells us that there is. So you would again say that the proof of Bertrand's postulate, Bertrand's theorem, is false proof because it's
Yes, so
It claims the opposite of what you said.
yeah, so it's an interesting question. So Peter is saying that there's a Bertrand's postulate, which is an accepted result that says that between any number n and 2n, there is a prime. So I think the problem is really having to do with the nature of existence. And when we talk about existence, we are in danger of stepping over into philosophy. The question of what does it mean for an object to exist or not to exist. It's a philosophical question, and I think that's the kind of thing that Jim's interested in. I guess what I'm saying is let's restrict ourselves to what we can write down. And I don't even, because I'm not sure what it means for something to exist, especially if that implies that it exists in some other world other than the one that we're actually in. Right, so to me, I'm taking a scientific point of view, and I'm saying I'm sort of like taking a 20th century physicist point of view. Let's restrict ourselves to discussion about things that we can actually observe, things that we can actually write down, and not even use the word existence. We don't have to use the word existence.
But there are things in physics which you have difficulty observing. This is what quantum mechanics is all about.
Well, maybe observing directly, but you can observe them indirectly. But if there's something that you cannot observe even indirectly, then I think most modern physicists would say that their existence is questionable. Yeah.
I have one question. What's the difference for you between the result of from array that you listed on advances on Goldbach Conjecture and the one from Helfgott?
The one from?
Helfgott? Harald Helfgott? That you didn't include in the list? Or did you? Maybe I was confused.
I don't think I had his thing in my list.
Yeah, so...
So I'm not in a position to
okay, yeah, no, I thought it was...
yeah.
perfect. You showed recently that with 3 primes you can get any number.
See, I would like to take these results, and I don't want to throw them away. I would like to reinterpret them as saying that they're really results about Hindu Arabic numbers that we can write down. Then that gives them a meaning to me that's more tangible, that they're not necessarily applied to things like 3 star n squared 4 or some of these crazy towers of exponentials. So I want to restrict our view of what numbers are to a more, what I view as more sensible, carefully constrained domain. And then hopefully translate those theorems into that more restrictive domain. Yes, Thomas.
Have you found any contradiction between your so-called common sense approach and or what you call Platonic approach? Have they ever clashed?
Have I found the question is, have I found a contradiction between this kind of approach and the Platonic approach?
Mathematics that you can imagine, mathematics that you can't imagine. Have they ever clashed?
Have they ever clashed? Well, I guess this whole argument here is in some sense an example of something where they clash, because I'm claiming that there is no prime bigger than z, but somebody who has a Platonic view says, yes, there is a number that's bigger than z, it just happens to be outside our universe. And so to me, yes, that's a big difference, but it's not a contradiction. It's in the same way that I cannot contradict hierarchies of angels. Maybe you believe in hierarchies of angels, which are also outside of our universe. I can't point my finger and say that there's a contradiction there.
So it's not that the mathematics necessarily is wrong, it's just what to believe.
Or maybe what position one has. Yeah, I think it has to do with the foundational position, which I think is very important. Yep.
Well, I understand you don't believe in the existence of prime bigger than z. Do you believe in the existence of composite numbers which are bigger than z?
I believe
In the existence of composite numbers
composite numbers,
which are bigger than z.
like 2z.
No, you can't write it, it's too much. You say z is the largest number you can write.
I didn't say it was the relevant. I wrote down 2z,
2 star z, it's just 2 extra zeros.
2 times z. I just write down 2 times 10 to the 10 to the 10 plus 46.
So what are the rules of the game?
Sorry?
What are the rules of the game? When do we
Well, for example, if we're working if you fix a particular system, let's say you give yourself so many symbols and so many operations, and you ask, what can you write down in this context? So then you've constrained yourself, and then some things you can write down and some things you can't. And so what I'm saying is that if you allow yourself all the digits and all these symbols for operations up to star 3 or star 4, you will not be able to write down a prime number bigger than z. That's my claim.
But assume the rules of the game say you can use 10 to the 10 symbols.
Sure.
And they ask you whether there are composite numbers beyond this.
So if I'm allowed to use 10 to the 10 symbols,
Yes,
yeah?
they ask you whether you can write a composite, whether you believe in the existence of composite numbers beyond this.
Beyond this.
Because now you cannot use 2, it's already one symbol too many.
Why can't I use 2?
Because it will be one symbol too many. You take the largest number, which you can write as 10 to the 10 symbols. And you cannot say 2 times this number.
Okay.
It violates the rules of the game.
No, but I'm allowing my symbols, like the symbols that I originally was using are the digits and the operations, but I'm allowing you to write arbitrarily long, I'm not limiting how long an expression you can write down with those symbols. Yeah, if your hard drive is big enough, you can write down some huge expression, no problem. So my assertion is that if your hard drive is the entire universe and you're able to write at Planck scale and you're able to use these symbols, you are not going to be able to write down a prime number bigger than z. And maybe that means that they don't exist or not. That's almost a philosophical question. I'm just saying you're not going to be able to write it down. And so you're not going to be able to write down 2z as a sum of primes. And so Goldbach just doesn't work. Yes?
So you have some problem with big numbers, right?
Yep.
What happens with small numbers?
What happens with small numbers?
Yes. So we can't do any analysis because we cannot write any small numbers.
Why?
10 to 0.
Say it again?
So if we try to consider some no limit tending to 0, so it somehow relates to very big numbers. So
It's dangerous to make statements that we can't do something. I mean, often one can do something, but one just has to think about how to do it.
how you can now consider some kind of a limit?
Well, certainly one can. If you watch my Math Foundation series, I explain how to do limits in a purely reasonable way.
So it's possible
It's possible, yeah.
to define integrals.
You could define integrals, yes.
But it will depend on the number of symbols.
I mean, you just ask yourself this. So, I mean, what does a computer do? Well, anything that a computer can do, a computer can't do an infinite number of things. No way. So anything that your computer can do is, in principle, you can model that, and you can model that in a finite prescribed kind of way. So your computer, it's probably true, your computer cannot calculate integrals exactly, but so what?
You call infinite. Computer can do infinite loops.
Well, I don't, you can press the run button and watch it loop. I'm not sure if it can actually finish the infinite loop. Any other questions? Thanks very much everyone for listening. And thank you for people. Oh, maybe I can say, excuse me, there are some nibbles and drinks up in